Thanks for all of you for being here. And I want to thank Dr. Arun Majumdar for inviting me to come and present at this seminar. 4 months ago, he basically bullied me into doing this. And he said, Stanford Energy Seminar is where luminaries in the field, leaders in the field come to Stanford to talk about big energy problems. And I said to him, then why are you inviting me to come here? But anyway, before this becomes a comedy routine, I'm really happy to be here. Most of my time here at Stanford is spent in the audience listening to enlightening lectures. And so hopefully this is a way for me to bring the world that I'm part of to the community over here at Stanford, because the problems that we're facing in the battery supply chain are tremendous and do need the type of creative thinking, the type of intelligent thinking that goes on at the engineering school, at the School of Geology, at the business school, at the law school over here for long-term solutions. If you have been paying attention to the news, it's hard to escape the fact that electric vehicles are a huge deal right now. And this is happening both from the side of the companies in the space as well as the major governments around the world that are pushing penalties, fines, subsidies for electrification. It seems like every single week we're seeing news articles out there about some country proclaiming bold proclamations around ending internal combustion engine vehicle sales, around reaching 30%, 40%, 50% EV by 2020, 2030, 2040, name your year. But the trend is clear. The countries want clean air, and they see electrification of transportation as a major way in order to achieve that goal. And the major companies in the automotive space are responding in kind with their own ambitious plans for battery electric vehicles. This is far greater than just Tesla, my former employer. This is a worldwide trend at this point. What that means is the battery has become increasingly important as an industry, as the largest cost component of these battery electric vehicles. So 5 years ago, there were 2 factories that produced lithium-ion batteries with over 1 gigawatt hour of production per year. And now we're tracking 121 of these factories that have been announced or under construction, and 52 out of these 121 are already producing today. Some of these companies have been around in the space for quite a while, but more and more we're seeing new startup companies, especially in China and Europe, taking on the burden of new battery capacity expansions. What's also interesting to note is China is the world leader today in battery cell capacity and will be in the future. If we look all the way out to 2029, we're expecting that fully 2/3 of the capacity for batteries used in electric vehicles and energy storage applications will come from Chinese companies operating in China. And that has broad implications for geopolitics that we'll discuss later. The growth in scale and the growth in size of these factories has resulted in an exponential decline in the price of battery cells. There are many other clean energy industries where this kind of exponential decline is seen. Solar is the one that's most frequently talked about, and many people are looking at the battery curve, the battery cost curve decline, and saying, well, this is not too dissimilar than what we saw 10 years ago with battery cells, with solar cells. The major push behind the cost reductions over the last 5 years or so has been from manufacturer efficiency improvements. So that's larger factories, more robust manufacturing lines. But increasingly today, cost management and supply chain of the materials themselves are becoming important, because we're starting to see diminishing marginal returns from just how much bigger you can make your battery factories, just how much faster you can make your manufacturing line. And we're also seeing changing consumer tastes around what specifications battery cells need, which directly impacts the quality of the raw materials that are going into these battery cells. And if we were to drill down a little bit deeper in talking about battery cells specifically, which, by the way, for those of you taking photos, there's a link that I'll put up in the last slide where you can download this whole presentation online. So if we were to drill down into what makes a battery cell, the cathode is the most important part of the battery cell from the standpoint of cost management and cost control. Your average lithium-ion battery that's being used for automotive applications, anywhere from 50 to 65% of the cost of making that battery cell is just in the cathode components. And most of those costs are in 3 elements: lithium, nickel, and cobalt. Yes, they're called lithium-ion batteries, and so obviously lithium is very important, but there are 100 different parts on average that are used to make lithium-ion batteries. And these three metals come out to the very top as being the ones that are sort of most interesting to watch, the ones that are most relevant to the whole challenge of cost management along the material supply chain that was discussed in the previous page. And this final point, short of vertical integration, short of a battery company or a car company going out there and buying a cathode facility or buying a mine, building more supply chain optionality, building more companies in the supply chain, developing more mines, more chemicals assets, is the best way possible to ensure that these material costs don't skyrocket in the future. So when we are thinking about the lithium-ion battery materials industry, these are the 6 key trends that I would argue matter the most. So the first is, not all battery cells are created equal. And there's a clear stratification of which companies can produce what battery cells at quality that's needed by Western OEMs. So the Chinese market for electric vehicles is approximately 50% of the total electric vehicle market today. But there's a clear difference between customer preferences for vehicles, which translates into the quality of the battery cells used in automotive functions in the West versus in China. So if you're a Western automotive today, if you're a GM, a Volkswagen, you're probably going to go out and source from the tier 1s of the world. Increasingly, we're seeing that these tier 1s can't do it themselves. There's going to be a severe shortage of what we classify as tier 1 battery cells today. So you're going to see more and more of these companies in tier 2 trying to jump up and trying to level up into supplying Western automotive to take advantage of those impending shortages. Those tier 3s, I mean, don't get me wrong, the tier 3s are important as well. It's just that they have to make a larger jump in their quality today to supply into the Western market. But to be frank, they really don't need to. The market in China, the market in places like India, which we'll discuss later, are big enough to justify a tier 3 automaker staying a tier 3 and just ensuring that they too reach that manufacturing efficiency improvement to push down their costs, not necessarily caring as much about the quality of their battery cells per se. And the final point that I'll make is this tiered structure over here. This is the core reason for why solar panels and the trends with solar panels and cost cannot just be projected onto battery cells, and why it's an unfair comparison to say that solar panels became commoditized, as a result batteries will also become commoditized. Why even invest in this space? This right here, the stratification between the products, the functionality between a tier 1 and a tier 3 battery cell, as well as that mismatch between supply and demand, as it stands today, is the reason why coming to the conclusion that battery cells are like solar panels and they're going to be commoditized, as a result why even invest in the space, is kind of a flawed way of thinking about this. Number 2, in the West, we have seen customers pushing for more range, more power, faster acceleration, my car is better than yours. That's the kind of attitude that drives Western automotive design decision making. So what that's translated into is we have many different types of battery chemistries. So over here in the top column, NCM means nickel, cobalt, manganese, NCAs, nickel, cobalt, aluminum, LFPs, lithium iron phosphate, etc. Previously, your laptop batteries, your cell phone batteries would have used something like an LCO. But now, because the battery performance in your car is so much different than the battery performance that you would need in a cell phone, you're starting to see more and more of these different chemistries and innovation amongst chemistries. From the customer standpoint, you're seeing customers push towards higher nickel use in the battery cells for their vehicles. Because, put very simplistically, when you have a higher nickel chemistry in your cathode, you can get more energy density, you can get more bang from your buck for individual cells. And the battery cell also lasts a little bit longer. So going back to the argument earlier of it's all about not just lithium, there are many other parts that matter. And specifically lithium, nickel, and cobalt are the most important for future battery chemistries. This is where it comes from. In that so many of the battery chemistries that are preferred by electric vehicles and energy storage companies, which are the fastest growing segments of battery consumption, rely on nickel-based chemistries. The one sort of dark horse over here is I've put a little bracket around LFP, where the this is where we see some differences between the Chinese market and the US market, for example, where LFP is kind of making a comeback in China. As of this moment, we don't expect that LFP is going to be highly penetrated in the market in places like the US and in Europe for automotive functions. But at the same time, we do see a possibility that more and more LFP will be used, partially driven by the performance of the battery, partially driven by impending shortages of nickel and cobalt. The capacity for LFP just exists today, and it's getting better. The chemistry is getting better as well. But the one commonality amongst all of these battery chemistries is the use of lithium. Hence, they're called lithium-ion batteries. In the future, so I always love to give a personal story for this. I own a Tesla. My dad owns a Tesla. I used to commute 40 miles one way to work. My dad commutes 4 miles one way to work. I wish I had his life. But we have the exact same battery pack in both of our cars. Why is that the case? We have different charging profiles. He lives in Houston where it's 150 degrees in the summer, and I live here where it's 80 degrees all the time. He charges at home. I charge at superchargers. I charge at ChargePoint here on campus. I don't have a home charger per se. And once again, I'm going through cycle life much faster than he is. So in the future, we're going to start seeing car companies separate the business model and separate the consumer offering for the vehicle body from the battery itself, to the point where in the future, you may be selecting a battery to go with the car rather than buying a car and getting a battery that comes along with it. And with advances in the lifetime that these batteries are lasting, you may be buying a car with a battery and in 10 years, throwing away the car body, holding on to the battery, and replacing that car body on top. It's mind-blowing today, I get it, but 15 years ago, electric vehicles were mind-blowing. So mark my words, it will happen. And if it doesn't happen, there's a YouTube video of this that you can use to keep me accountable. But within individual companies, you're going to see differentiation by application for each of these different chemistries, where in the future, my car, the battery chemistry in that car is going to be different than the battery chemistry in my dad's car. It will be different than what my uncle in India would use. It would be different than what my aunt in Singapore would use. It would be different than what my business partners in England would use. The next trend comes to the supply chain. Part 2 of this presentation will drill down a lot deeper into this topic. But if we were to look at the cathode supply chain and those 3 critical elements, lithium, nickel, and cobalt, that feed into cathode, it is overwhelmingly clear China is the leader in the capacity. Chinese companies have established themselves as the leader for building the capacity in these markets. Now, because of the fact that so many Western automakers are growing their EV offering, we're expecting to see some shift of this capacity away from China and towards end markets. That doesn't mean that China is going to stop investing in these markets. It just means that Western automakers are going to wisen up and say to their suppliers, we want co-located manufacturing along with our battery plants and our vehicle plants here in the USA. Part 3 of this presentation is going to be all about strategies related to national strategies around battery supply chain growth and the types of thinking that those of us who are interested in interdisciplinary thinking between business school and law school and engineering can accomplish. And then major trend number 5, if you were to look at what it takes for a lithium atom to go from the ground to going into your car, these are the high-level steps. You have to mine it, you have to process it into a specialty chemical, then you have to produce a cathode with it, then you have to produce a battery cell with it before finally it can go into your car. The timeline to build new capacity in each of these steps of the supply chain is very different from one another. The biggest problem is that step number 1, mining, takes way longer than basically all of the other steps. I mean, the best case scenario for developing a mine, absolute best case scenario is 5 years. But you're looking at 20 years to do exploration campaigns, to develop a mine fully before that thing even starts to produce anything of value. And even when it starts producing, it may not necessarily be valuable to an automaker in the future. And because of that dislocation between the first step and the last step in the supply chain, we're starting to see some of these worrying trends, like we have on the right-hand side of this page, where if you look at the lithium chemicals market for supply and demand, there's just no two ways to cut the story. We are going to be in severe shortage of lithium. And there are similar charts for nickel and cobalt chemicals, but this is the one that's the most striking. And once again, you can't go away from lithium. You have to use lithium for lithium-ion battery. So oftentimes I get the question, well, you can throw away lithium if you throw away lithium-ion batteries. That's just not going to happen because of what we discussed over here. So much investment is going around lithium-ion battery and building factories and manufacturing lines because this technology has been proven on a commercial scale for so many years. At a commercial scale, since the start of laptop batteries and cell phone batteries, it's taken 30 years for the arc of technology development in lithium-ion batteries to reach the point where this kind of investment is going in. So while there's a lot of people talking about solid state and how solid state is better than lithium-ion on a lab basis, I completely agree with the scientific results that say that other forms of battery chemistry may be better than lithium-ion when it comes to performance in a lab. But from a business standpoint, if you're the CFO of a battery company and you've just paid billions of dollars to invest in a manufacturing line for lithium-ion, you're not going to walk away from that investment anytime soon. So lithium is here to stay. This chart on the right should be keeping up executives at GM and Ford and Volkswagen and battery companies like Panasonic and LG and all up at night. So the entire second part of this discussion is just about the lithium industry. I'm going to pause here just for 2 questions before we move on. We'll do a broader Q&A at the end, but I figured if I talk for 50 minutes, I'll get tired and you guys might fall asleep. So any questions on part 1?
How many cars, trucks, just how many, out of that 2 terawatts, how many vehicles does that cover?
So an easy way to think about this is, an easy comparable is Tesla, 35 gigawatt hours for the Nevada factory was designed for 500,000 cars per year. So you could basically use that and scale it up to 2 terawatt hours. Now there's a few differences. Number one, Tesla vehicles have more kilowatt hour per pack than other vehicles. Second of all, not all that battery capacity is used for vehicles. Some are going to be used for energy storage applications as well. So there's not a direct answer to your question, as much as it remains to be seen what is going to be the split between automotive and energy storage. Order of magnitude ballpark at this moment, something like 80% of these battery cells are expected to go into lithium-ion for automotive. And the reason is because recycling of lithium-ion battery cells is expected to fill in some of the gap for energy storage, because the performance criteria for what you need your lithium-ion battery to do in grid-scale energy storage is far less than that of...
What percent of the total fleet globally does that?
Okay, so if you were to look at this over here on the unplanned new supply, we're expecting that the demand is from reaching about 15% of global vehicle sales by 2025 and 40% by 2040 of global vehicle sales. Global vehicle sales right now, this year was 100, last year was 110 million vehicles. That's expected to grow at GDP growth rate. The only thing that could stop that from happening is how far autonomy advances and whether or not autonomy is going to have an impact on car ownership and car purchasing around the world. But I mean, that's a framework to solve your question. That didn't directly answer your question with a number. I'll take one more question before we move on.
So you mentioned there's going to be this huge new unplanned supply that we aren't going to be able to meet with lithium shortages. And you also said we're not really ready yet for solid state or anything. So what technologies do you expect to slack shortage?
Yeah, so I could give a 45-minute presentation just on recycling. And the short answer is we're going to have to see more battery recycling capacity. We're going to have to see more materials recycling capacity. And I think the next part will also talk a little bit more about what can be done from a technology standpoint to solve this. So with that, I'll go to the next part. And we'll talk, anybody who has more questions, we'll talk at the end. I just want to keep things moving along. So lithium chemicals industry. Lithium industry is a super exciting industry. Lithium is everywhere in the world. It's in the water, it's in the oceans, it's in the land, it's in your face, it's in the air you breathe. That doesn't necessarily mean that all of that lithium can be economically extracted. So according to the USGS, these are the countries where you are most likely to find lithium that can be economically extracted along with the reserve and resource data. So just for semantics purposes, just because a country has lots of lithium resources doesn't necessarily mean that that lithium can be produced. So Bolivia is a great example of this. Bolivia, lots of lithium resources. You can go to the Salar de Uyuni as a tourist and see, literally you can pick up the salt off the ground. Lots of lithium resources. Doesn't necessarily mean that with today's technology, it's economic to produce battery-grade lithium materials or lithium chemicals out of that material in Bolivia. And there's a few reasons for that. The main is contaminants, but just keep that in mind. And what this results in is that there's sort of a concentration and oligopoly of a few countries where both the mine and the chemical supply of these materials come. So once again, the biggest difference between the left-hand side and the right-hand side is, who's the biggest country on the left-hand side? Australia. Who's the biggest country on the right-hand side? China. The mine is where the mine is. You can't just invent a mine in the ground. You're going to discover it where it is. But going back to the point made earlier, China and Chinese governments who are operating in China have done a very effective job of filling in the holes in the supply chain where they may not necessarily have primary resources. It's also interesting to note that this slide doesn't talk about is not all of that mined capacity in Australia is mined and owned by Australian companies. Chinese companies who are in this chemical stage have been very good at making investments in the mining sector in Australia to secure their supply of these mined materials for those chemicals as well. If we were to drill down from a country level to more of a company level, and we were to think about who are the companies that can supply lithium-ion battery makers, if you just do a Google search for lithium companies, you'll get 450 results. But this is an extreme Pareto in action over here. There's 5 companies over here, Albemarle, Ganfeng, Tianqi, Livent, and SQM, which account for basically all of the lithium chemicals that are going into batteries today. And that oligopoly is expected to continue. And their concentration of assets right now is once again in those same countries highlighted in the previous page. So while these companies are making investments in other new countries, the resources are just so rich in Australia, in Chile, and Argentina that it doesn't make sense for them to go out and develop resources anywhere else. So we're going to see not only these companies continuing their dominance in supplying tier 1 automotive grade lithium-ion battery makers, we're also going to see that these countries are going to be where the lithium material is originating from. 2 major ways in which lithium is made. It's not traditional mining in the sense that there are brine and spodumene deposits. So a brine deposit is mostly what you're going to find in South America. And the way I would think about brine deposits is you basically pump out salty groundwater and you let the sun do its work for 2 years to evaporate away the water. And what you're left with is a concentrated brine solution. I mean, talk about technology from like the 1950s, right? But that's still what's used. And this photo right here is from SQM, one of those big companies. It's in Chile. And those are their brine ponds. And that occupies more space than the island of Manhattan. Yeah. And so this photo in the bottom right, this is a photo that I took on a visit to a brine pond somewhere in the world. And you can actually see that these pools are quite massive. I mean, like, I put this photo up because you used to be able to see a person in the photo, and you can't even see it now. But that's just for scale comparison, just how massive these pools are. On the right-hand side, you have a traditional spodumene mine. So this looks just like what you would think of mining. You cut a huge hole in the ground, you pull out dirt, and then you concentrate that dirt to find out what resources there are in that dirt. This is mostly in places like Australia and Brazil. And this mine over here is the Greenbushes mine in Australia. This is a 130-year-old mine. So to get to that scale and that size, and for this one, you can actually see the scaling a little bit because you can see that truck in the bottom right-hand corner driving up the mine. It's taken 130 years for them to dig up this mine. This wasn't always a lithium mine. It's not like there were lithium-ion batteries in the 1890s when this mining started. What they were looking for was tantalum and tin. And then this mine became a huge supplier for Allied nations during World War II for tantalum and tin for defense purposes. And they would literally throw the lithium away at that time. And then as time shifted, they realized, wait, we can actually make a lot of money off this lithium. So, and you're seeing that with the brine ponds as well. SQM was a big potash company. And I wouldn't say that they were throwing away the lithium, but it wasn't necessarily the most important product for them to produce. But times have changed, things have changed, and now lithium is the primary product out of deposits like this for both types of deposits all over the world. Two major products of lithium that are used in battery manufacturing, lithium carbonate and lithium hydroxide. If you guys are into chemistry, Li2CO3, LiOH. There's been a push towards more LiOH, lithium hydroxide, because it's more suitable for the use of high nickel cathode manufacturing. But both are still very important. Both are continuing to be equally important. By 2025 to 2030, you're going to see a 50-50 split between these materials. What's been interesting is the price for the two materials are quite different from each other. There's always been a premium for hydroxide over carbonate, because for the longest time, the carbonate market was just so much bigger than the hydroxide market that a lithium manufacturer would manufacture carbonate and then take a small portion of that carbonate and convert it into hydroxide at approximately $2 per kilogram, and then they would just pass that on to the customer. We're seeing that this band between the two prices will start to narrow quite a bit, because now, with the fact that lithium hydroxide is growing in its concentration of the end market, there's going to be more innovation in going directly from mined product to hydroxide. And that's going to be the preferred route for most of the companies that we were highlighting earlier, rather than going from brine to carbonate to hydroxide. What we're seeing also is that because there's a huge explosive growth in this industry, the contract structures in an industry like this, from a business standpoint, were pretty straightforward for about 25 years. If I'm a lithium maker and you're a customer, I'm going to make a bag of lithium, I'm going to sell you this bag of lithium, you're going to pay me a price, and that's pretty much it. And once again, I never cared about that bag of lithium, because what I was actually trying to sell was the tin, or the tantalum, or the magnesium, or the potassium, or you name it. Now, because lithium is the primary product, and because so much investment is needed in lithium, we're seeing interesting new business models pop up across the supply chain. And this is just one example that some of the MBA friends that I have over here can kind of nerd out about, where previously, Sigma Lithium, so Sigma is a Brazilian company, and it's run by two very good friends of mine. And previously, 10 years ago, all they would care about was selling spodumene rock, literally just rock, to somebody in the middle, and they'd be done. Now they have to care about where does this material go all the way. So they partnered with Mitsui, who's a huge Japanese trading company, one of these trading conglomerates that was responsible for the iron ore boom in Australia, the nickel boom in Southeast Asia. These Japanese trading companies have been instrumental in commodities booms over the last 70 years in the Eastern Hemisphere. So they've partnered with them, and they're looking all the way down the supply chain. And they actually got a prepayment of $30 million to finance their plant. So once again, going all the way from I sell you X and you buy X and you pay me Y, to creating true partnerships along the supply chain, because the companies see the opportunity. They see the fact that there's a huge value opportunity, a huge profit opportunity in partnering along the supply chain to be part of this huge growth. But, and I can show 5 or 6 different examples like this, but that's not the point. The point is, even though you have a lot of business model innovation like this, you are still going to see these severe shortages. And usually, in MBA school, we would call this an arbitrage opportunity, right? You're seeing huge demand, not a lot of supply. What do you expect will happen? Price will go up. Great, that's my first microeconomics class right there, summed up. So you would think, hey, price is going to go up. I should invest in this. But that's not what you see happening. You don't see investors flocking to this material like they would, software-backed companies over here in Silicon Valley, for example. And if the industry takes a step back and reflects, I would say that there's 5 core reasons for why this is the case. So the first is, who is going to want to invest in materials like this? Traditionally, who invests in materials like this are people like mining investors or chemical investors. So in Silicon Valley, startups care a lot about growth. If you're a mining or a chemicals investor, you care about one thing and one thing only: cash flow. In order to make cash flow happen, you need to have predictable prices in the long term, publicly traded prices that can be capitalized, that can be hedged, betas for these stocks that can be easily understood, and none of those are true in this industry. It's very much still kind of a cowboy industry. So in lithium, for example, in any sort of major material, let's take nickel. There's been a boom, there's been a bust in nickel that's lasted for 11 years, which is pretty normal. In mining, they call these super cycles. So like aluminum super cycles will last 25 years, like a boom and a bust. Iron ore has just been sort of booming constantly for the last 70 years at this point. Lithium has seen a boom and a bust in just 6 years. And this kind of thing scares investors away, right? Like they're not looking at a chart like this and they're not saying, hey, in the long term, there's a huge arbitrage opportunity over here and the prices are going to go up. They're looking at this and they're saying, I don't know what my cash flow is going to look like because I don't even know what prices look like over here. So that's scaring them away from wanting to make that investment. The second is, when it comes to mining, as it comes to any resources industry, the best player is the player that can guarantee the lowest operating cost of production over the longest period of time. Some of the best deposits are already taken over here. So in the leftmost part of this chart, we see the Greenbushes mine that we talked about. And what you want is to find a deposit that mimics Greenbushes as much as possible. Greenbushes is a freak of nature. You're not going to get something like that again. But you want to mimic those characteristics. Low operating cost of production with as much resource as possible. And truth be told, it's getting harder and harder to find mines like this in the world. So if you're an investor, the first question you're going to ask after trying to solve the price problem is you're going to say, well, how do you compare to the best-in-class brine asset? How do you compare to the best-in-class spodumene asset? And if you're not as low as possible on this curve, then you're going to have some issues. So let's say who's pretty low on this curve. You know, Araçuaí is that mine in Brazil from Sigma that I had mentioned earlier. Hombre Muerto is already producing in Argentina. Pilgangra is from the Pilbara in Western Australia. And then as you start going up, Salar de Atacama is producing, Mount Marion is producing, and then you get to a point where it's harder and harder to find producing mines. There are still a bunch on the right-hand side that are producing today, but it's just harder to encounter them because those are not nearly as investable as those on the left-hand side of this chart. And unless you can find a new mine that you can prove sits on the left-hand side of this chart, you're going to be facing a little bit of an uphill battle when it comes to investability. I think this might have accidentally turned off. So number 3 reason, just because you can produce lithium doesn't mean that your lithium chemical is going to be used in battery manufacturing. So if you were to, the way that I would think about this is, if you were to dip your water, a cup of water into the river, would you necessarily drink that, or would you trust the water that comes out of your faucet or your tap more, that's been certified to be free of contaminants? Well, that same sort of certification process happens across battery materials. It's a process called qualification. It is extremely complicated. So your Teslas of the world, your VWs of the world, but also your LGs and your Samsungs of the world, what are they scared of? They're scared that that battery in that car will fail, that there will be a fire, that it'll hit the news, that they will be on the hook for all sorts of warranty claims, all sorts of legal claims. And so what they do to defend against the possibility of this happening is go through a rigorous process of qualification to ensure that all the materials that are being used in their battery cells have the highest specification possible. Now you're talking about plants that are $700 million US dollars of capex to build, producing tens of thousands of tons of lithium chemicals. And what the end user is basically saying to these plants is, we want to see you produce 99.99% lithium hydroxide at parts per billion in purity, over and over and over again, 24/7, 365. And we want to see that today, we want to see that tomorrow, we want to see that a year from now, we want to see that 5 years from now. That is a really hard challenge for chemicals companies to go through. And don't get me wrong, they do get help along the process from the end customer and the end user, but this process to qualify and the lack of a guarantee that just because you produce, your material will be used in the supply chain is something that also can scare off investors sometimes. Issue number 4, there's tons of articles out there, which I call like tremendously fake news articles, about how don't buy EVs because EVs are dirtier than internal combustion engine vehicles. This is kind of a half-truth. So Volkswagen did a very public study on this to negate some of the haters. And as you can see, in the lifetime of an electric vehicle, you're going to do better than a diesel car. But the one part of this that's prominent is when it comes to the vehicle production, the cradle to gate for EV production does have a higher carbon footprint, has nearly double the carbon footprint of producing a diesel vehicle, even before it leaves that factory gate. So there's some truth to the criticism, even though the overall criticism is just flat out wrong. The reason for this is because diesel cars, petroleum cars, internal combustion engine cars, these are supply chains that have developed over 130 years. There's already been 130 years of cost-cutting efforts. There's already been 130 years of innovation. There's been like 5, 6, 10 years of innovation for the battery supply chain. I mean, at the level that we're seeing the battery supply chain, once again, 5 years ago, there were 2 factories at over 1 gigawatt hours of production compared to 120 now. So that same level of innovation, especially when it comes to carbon footprint, especially when it comes to using cleaner electricity sources, better reagents, just hasn't happened yet in EVs. Doesn't mean that it's not going to happen. We see now an increasing push from your major global automakers to try to push down the carbon footprint of their supply chains because they're facing environmental activist pressures, they're facing consumer pressures to show that even beyond the lifetime of the vehicle, we want to show that producing our electric vehicle, cradle to gate, just vehicle production, just that dark blue line, is as good as, if not better, than your internal combustion engine vehicle. And if we were to drill down deeper, the carbon intensity of, even within lithium, for example, and this is data that comes from 3 very good friends of mine, Alex, David, and Robert. Brines versus spodumene, there's a huge difference in the carbon intensity. That's not just driven by the process to make these materials. That's also driven by what are the electricity sources in Chile, in Argentina, and Australia. What is the reagent availability in these countries? It's a lot more complicated than just saying, okay, we want to go carbon-free. Let's find a way to go carbon-free. Because we're dealing with national governments here. Shutting down a coal-fired power plant in order to ensure that you can use solar for Australian spodumene production goes well beyond just the company making the investment. I mean, the government of Australia comes in and says, well, we don't really want you to lay off 500 coal miners from work. We don't really want to shut down a coal-fired power station. So no, you can't do this. You have to find a way to reskill and retool those people. So while there's a lot of initiative, while there's certainly a need from environmental activism and from the car companies themselves to push down that vehicle production carbon footprint, it's going to take a lot longer because of some of these sort of geopolitical implications that an action like that has in the supply chain. Finally, for those of you engineers in the room, you'll recognize this process flow diagram. I went to engineering school 5 or 6 years ago, and this scares me just looking at it. But the truly scary part about this process flow diagram is there hasn't really been much innovation in the way that lithium chemicals have been made in about 50 years. This process flow on a commercial basis has not changed much. On a lab basis, there's a lot of effort. Even here at Stanford, there's a lot of effort in terms of new ways of making lithium chemicals. But if you were to ask one of those big companies like a Ganfeng, a Tianqi, what they're going to say is, we have to invest so much capital into these projects to produce for 30, 40 years. We don't have the capability to do a complete overhaul as much as we do to do continuous improvement on our current process flow diagram. But the difficulty over here, and why investors kind of fret when they see something like this, is even just looking at some of the elements. So acidic sulfuric acid, that is tremendously environmentally corrosive. And yet it's very necessary for the production of lithium chemicals using this spodumene flow sheet. The electricity costs for the ion exchange purification, for electrodialysis, for the multiple precipitation steps that need to happen, I mean, these are huge machines that use megawatts of electricity. These aren't simple problems to solve, once again, when we think about the electric grid that feeds into these projects with industrial PPAs. And then finally, previously, we've had issues around byproducts and what kind of revenue they can generate off of byproducts. Because you would think, well, I see many different steps where there's precipitated impurities coming out, where there's multivalent cations that can be used in different salt markets coming out of this process flow. Why isn't there a secondary market for these materials to offset some of the R&D expense in order to improve the carbon footprint, in order to improve this process flow diagram? The answer is that those industries just aren't big enough as compared to lithium. That's not true of everybody. This is a spodumene flow sheet. So if you were to look at a brine flow sheet, you'll see KCl coming out, you'll see calcium chloride coming out. There are big industries for chemical consumption for those as well, but those are outweighed by just how fast lithium is growing. So once again, end of part 2. I'll take 2 questions before I do the final part.
You didn't mention the new extraction process. You haven't mentioned too much the new extraction process that are off to extract more from brine or geothermal brine. Could they allow higher speed project to come online with different sources?
Do they allow what?
New project to come online, spotting different sources that are not targeted today and faster?
Yeah, absolutely. So I think 2 weeks ago we saw Lilac Solutions did their fundraise and they made a lot of headlines from that. And that solves, earlier I cheekily said like brine technology, making brine ponds that are bigger than the island of Manhattan. This is technology from the 1950s. And solving that challenge, companies like your Lilac, companies like EnergyX, but even companies like Suez or Veolia, they're looking at how to solve this problem. There is a space not only for innovation in the extraction of these materials, but also in the efficiency. So today, those brine ponds, you only end up recovering about 40 to 50% of the lithium in a brine pond before that water gets pumped back in. I mean, it's tremendously wasteful, that kind of process. So even in a continuous improvement standpoint, from the technology that we have today, there's a huge opportunity for improvement in efficiency. Take one more question for the final part.
This portion, you talk about carbon footprint, how it is affecting ice or diesel versus electric vehicle. But there are other factors that are coming with the ice engine and diesel engine. The fuel system that is in the vehicle, air induction system is gone. So there are 4, 5 systems that will not be there in the car in favor of the electric vehicle. So the carbon footprint from those is also reducing. So it may be a bigger picture of carbon footprint if you compare and add everything.
Yeah, I love that. For those of you who couldn't hear, basically the gentleman was saying, you can't just take ICE technology and say, take ICE and add battery to it. There's so many changes that'll happen in the design going from ICE to battery electric vehicle that because of the fact that so many systems like air compression, like induction systems will be replaced with new electrified systems, the carbon footprint will be decreased. So great comment, really appreciate that. I have 5 minutes and my last part is only about 5 minutes. So, I promised earlier, I mentioned what can we do to grow an international supply chain? What are some of the steps that governments are looking at? And yes, 50% of the market is China, and China has huge penetration when it comes to the supply chain. But a lot of these governments that have announced ambitious electrification plans that are home to a traditional internal combustion engine economy today are also taking steps towards localizing a supply chain. And this is kind of what I do most of my time is, governments and government ministers call me up, call my business partners up and say, hey, we want to attract a chemicals company. We want to attract a battery cell company to come and set up operations over here. What should we do? And is it even worth it for us? So the answer for is it even worth it is absolutely yes, but it depends on what part of the supply chain you invest in. From a margin standpoint, car making is an atrocious business. Margins are always on the decrease. It's tremendously brutally competitive between different car companies. So what we suggest is look further upstream. Look at things like chemical processing and cathode production. Yeah, the mine is where the mine is, and you're not necessarily going to be able to move a mine geographically. Like, that's not possible according to laws of physics. But you can build chemical processing facilities anywhere in the world to convert those mined materials into a chemical that can be used for automotive manufacturing. And the value multiplier is just absolutely massive. But beyond the value multiplier, beyond the operating profits that can be used for taxable revenue base, what politicians love more than anything else is jobs. This is a huge job creation opportunity. And this is what we try to say when we're here in the US. So 6 months ago or so, I went to the White House with this slide. And I showed them, guys, why are we caring so much about building more car plants over here when this creates 1,500 jobs potentially with a taxable revenue base that's far greater than what you may get from individual car manufacturing lines. And it's almost like a light went off in the room and people finally got it. The investability of this problem goes far beyond just the cars and just the batteries, but down to the battery supply chain as well. For the US, considering that we are here in the United States, Stanford is a very American institution. I am very American. The US has done a very good job of building an automotive sector over the last 130 years. The US has also done a very good job of attracting battery makers over here. My challenge to our lawmakers, my challenge to those of you who go and work in chemicals industries and battery industry here in the US is help us fill the gap on those first 3 steps: mining, chemical processing, and cathode production. We need those steps to also be invested in over here in the US. We need more of that capacity outside of China, just in general, for geographic, geopolitical diversification. But we also need to create jobs here in the US. And the final point is the battery industry is here to stay for a very long time. Electric cars are here to stay for a very, very long time. And all of these industry trends and some of the scary statistics that I said shouldn't preclude the fact that we are very much in a race for clean air around the world. This supply chain has to grow along with the vehicles, along with all of us who are excited to buy electric vehicles. And the final point is it's going to take people like those of us who are in this room today to think of new business models, to think about new flow sheets, to think about new scientific, physical, chemical processes to create the innovation that you need in this space. So if you have any questions, there's my contact information. If you want this presentation, please don't email me. Pull out your smartphone, go to the QR code, follow the instructions, and you will be able to download the presentation over there. So I think I'm out of time. Thank you.